Hi, we are the HRS Plate Settler sub-team. Our overarching goal this semester has been to run sedimentation processes at higher upflow velocities to achieve better flock blanket longevity and quality. Previous HRS sub-teams have tried to achieve this goal by many calculated attempts, including incorporating a flow recycle line from the top to the bottom of the sedimentation tank. While this proved ineffective, this led to our work this semester. And right now we've been working on designing and fabricating a plate settler's apparatus to incorporate into the sedimentation tank in the graduate students' lab.
Yeah, so this leads us to our previous work. We've had a couple done on this, working with the sed tank. First, we're going to start with Matt Hurst, who looked at the velocity gradient and the residence time of a particle, and he held that value, that constant product at around 20,000, and then looked at the NTU as a result. They gave us some good variables to start with, including our alum dose ranging from 1 milligram per liter to 7.5 milligrams per liter, as well as a 1.1 millimeter per second upflow to 1.2 millimeter per second upflow. Additionally, we looked at CULP and the angle alpha and seeing how we should vary that angle of the plate settler, and that gave us some starting variables as well. Furthermore, Casey Garland gave us some great manuals and ways to work with that sed tank, and just gave us that documentation necessary to get this sedimentation tank working. And then that leads to the actual testing, in which the summer 2018 looked at the density of the flock blanket and its distribution, and seeing that it was more concentrated towards the bottom rather than the top, which led to that flock blanket breaking, and that gives us a purpose as a sub-team to look at that density and see what plate settlers can do for that. So that leads to HRS flow recycle, in which they tried to establish a flow recycle line, which kind of recirculated those flocks, and then that eventually lead to us as a plate settler team and trying to fulfill that common end goal of fixing that density.
So here's a picture of the sedimentation tank in a full-scale aquifer plant in Las Vegas, Honduras. And as you can see here, the sed tank is large. So the thing is, we want to increase flow rate to decrease tank size and lower effective cost in like the grand scheme of things. So the problem is that previous HRS sub-teams have found that the flock blanket tends to fall apart a few hours into experimentation at higher flow velocities. So the various attempts we've been making are to see, like, okay, will this design fit and also let the sed tank work at a higher flow velocity, and varying just different variables to see how close we can get to this overall goal of increasing the flow rate to decrease tank size and lower effective cost, all while maintaining an effluent of no higher than 0.3 NTU. And here's the sed tank model. This is just a schematic of how water flows through the actual sed tank in the plant. So water will come in through the manifold diffusers and go through the flock blanket, which is a stabilized, fluidized bed of flocculated particles with an effluent clear layer above. Water overpours the flock blanket and goes into the flock weir, and any small particles that aren't that go over the flock weir and the flock blanket are captured by the plate settlers. And the velocity at which they are caught by the plate settlers is called the capture velocity, which is going to be explained in a few slides, but basically is the lowest velocity at which the plate settlers capture the particles.
Here we can see the actual sedimentation tank we've been working in at the lab. This is pretty much scaled down model of the actual sedimentation tank that they use in the avocado plants. Now I'll explain some parts of it. First, we have the jet reverser, which is pretty much a small tube in the right of the tank. That's where the water first comes in, and its position in the tank is really important because the way the water flows through it, it helps get rid of all the flocks that settle at the bottom of the tank and put them in suspension again. Next, we have the plate settlers, or in this case, tube settlers. These have a really important role in the model because when the water flows up the tube, all the little flocks settle at the bottom of the tubes and then just slide back into the tank, and that way the flock blanket can be formed. Then we have the flocculator. This tubing system simulates the actual flocculator that we would see in a big tank. And that's where water flows through before going into the jet reverser and coming into the tank. And lastly, we have the flock weir, and that's where we have a tube that pumps water out of it.
Yes, as you can see, we've installed some new tubing and got the said tank up and running again. So if you look to the left of figure 8, you actually have our influent and effluent turbidity meters, and those are just measuring what's going in, what's going out. Influent is pumped by that influent pump to the right that you see. That's working at about 143 milliliters per minute for 1 millimeter per second of upflow. Then as well, we have our clay, which is being dosed, controlled by the PID and controlled by Procota, so that's dependent upon the influent. And then lastly, we have that pack dose, which works at about 29 milliliters per minute to establish that flock bed. Lastly, when the water all comes out, it goes to the tube settler pump, working at 94 RPM, is measured by the effluent, and then goes to the drain. Furthermore, we have a sponge for cleaning the tank, as well as a camera setup to do any qualitative visual data necessary. So yeah, move on to that next slide. We can talk about our choosing configurations, in which we use Python to find those previous values. And those were just done by calculations either through, as aforementioned, Python, or experimentation and Python, in which we experimented by using graduated cylinders to find those values. So for example, taking the RPMs and taking the outflow that was caused by the RPM, controlling that relationship using a proportionality and relating the two.
Coming back to plate settler theory, this is just a slide to describe how capture velocity is derived. So capture velocity is the velocity of a flock that is only barely settled out or captured by the plate settler. And here, looking at the first and third equations, we can solve for the capture velocity, where L is the length of the tube, since this is applying the capture velocity model to a tube settler, not a plate settler. So L would be the length of the tube, D would be the inner diameter of it, and then V up would be the vertical velocity through it, at an angle of 60 degrees. And our alpha angle is what we are varying. So right now, as the plate settler subteam, we are using an alpha of 45 degrees, and hopefully future subteams can experiment with the plate settler orientation and try some different angles to see if there's a more optimal orientation of the plate settlers during testing.
Yeah, so speaking on that modulation, that modifying of it, we wanted to go with the design that fixes that. So we can just talk about them a little bit. As you can see, we have our model and mock in here, but
Our main goal this semester was achieving a flock blanket that it has the same density in all points in the tank. And we thought that including a new row of plate settlers would increase the area in which the flocks can settle. And then that would lead to a more stabilized blanket. So that would be our best possible outcome in here.
yeah, so this is the design we're working with. As you can tell, it's we have our modulated system. It's a ABS plastic insert that can slide in and out. We are able to change the angle of this, working with that 45, just because that gives the longest possible trajectory through the plate settler. So our design is actually 340 millimeters long, which is the size of the tank, as well as 14 millimeters in width, so it can slide in and out. The idea was to reduce scratches, get the most sedimentation possible through that with the least interference. So we just wanted to make this for proof of concept. Sadly, there was a lot of residue plastic, so we had to move on to something new. So that new approach was to put a drop line between it and actually hand fabricate it. So we have knots along that wire which tie the angle and hold it at that constant angle we want. And furthermore, we are able to slide them on and off as necessary to change the number, change the distances in between, and just still work with that very modulated, modifiable design. The overall goal was just to minimize the sedimentation interference, which is why there's only one drop line. That being said, this still led to some problems.
So we thought we should mention some of the ideas we had, but we didn't have time to try for future teams. So one of the main ideas was trying, instead of having one wire, trying having two, because we thought that might be easier for setting the angle at which you want the plates to be. Maybe trying different kinds of wire, maybe a stiffer one that it's easier to work with. Also, we had some trouble with the latching device at the right side of the tank, and because that with the wire, the way it was pulling, it wasn't stiff enough, so maybe finding like a metal material that would make it stiffer. Another thing is that for making it watertight and also easier to slide in and out, maybe putting some sort of silicone or plastic material at the sides of the plates and the latching devices would make it easier, and that way we wouldn't scratch the glass of the tank. Another thing we thought of was adding a second pump to the tube settler so we can pump water out of the tank quicker. And finally, we think that future teams will have to actually open up the tank and fix some of the parts in it, because we found some leakage from the tank to the flock weir, and we think that should be changed. Overall, just trying different materials, thickness of the plates, distance between the plates, different wires, and that's basically it. If you have any questions or recommendations, feel free to let us know. And here we have our appendix slides.
Thank you.